Welcome back. We are now going to, I think today we're going to try to just finish up what we wanted to do. We wanted to accomplish a goal in the very beginning of our journey into geometric algebra and space-time algebra. Our goal was to unify Maxwell's equations, meaning I wanted to take, let me see if I can find it here, I wanted to take the four vector Maxwell equations that we all learned as undergraduates or in high school, these four vector equations using the classic Gibbs Heaviside vector formalism, where the magnetic field is a vector and the electric field is a vector, and we just deal with the fact that one of them flips under a change of coordinates. One is a pseudo vector and the other is a vector, for example, polar vector and axial vectors, right? We deal with all that, but we treat everything as vectors, and we have four equations that describe the electromagnetic field. And we compress that into two equations using the formalism of exterior calculus, right? So now we have df equals 0 and the Hodge dual of the exterior derivative of the Hodge dual of the electromagnetic field form is equal to the current one form. So this is let's see, this is a two form. The Hodge dual of a two form is a two form. The exterior derivative of a two form is a three form. And the Hodge dual of a three form is a one form. So this is the one form. Sometimes, by the way, you'll see it written like this without that first Hodge dual. And in that case, the current is defined to be a three form. I think Wikipedia actually does it that way. Anyway, so we got these four broken down into two, which is nice. And then there was another section where we were also able to break it down into two equations using the Lorentz invariant relativistic formulation of electromagnetism with the electromagnetic tensor. And we got it into two expressions. And also, I think you'll often see this second expression, which is kind of complicated by this strange notation of a fully anti-symmetrized sum. But if you take the dual of f and create g as the dual of f using the standard prescription in tensor calculus for creating a dual, then you end up with a nice simple form. So you end up with just this guy and this guy, right? And remember, our goal was to then take these two, we found it, broke it down into two mathematical formalisms that have only two equations for Maxwell's equations. We're wondering, could we make it one? And could we compress these two into a single one? And the answer is yes, and the answer is geometric algebra. And we started our journey in geometric algebra with that goal in mind. And we studied our geometric algebra, but now it's time to just get to this goal. The problem is, however, there's still quite a bit between us and the goal, right? This entire section about space-time calculus is actually it's very rich. And I think, though, that instead of going through it with as much specificity and detailed formalism as we did in the previous sections, we're going to kind of cut to the chase a little bit. And I will consider doing the heavy formalism stuff in a separate series of lectures just on geometric calculus. Because geometric calculus is a fascinating subject in and of itself. But we can actually get to Maxwell's equations in a vacuum and Maxwell's equations with sources, which is our ultimate goal, taking all of Maxwell's equations and compressing it into one statement without studying this section on potential representations and without really digging too deeply into space-time calculus as it's presented here. And by the way, as it's presented here, it's a little too much. This paper is a review paper that can't possibly teach space-time calculus in a full and robust way. And we would have to leave this paper for a long time and then come back, and then this would be super anticlimactic. So we're going to try to compress this entire section into this lecture and just cut to the chase, and then come back and address the formalism in another section of lecture. So we can think of this as a high-level view, but we're not going to be trivial about it, but we're not going to go into the full depth and detail. Okay, so let's begin. I'm going to just begin by defining the important object. this del operator in geometric calculus. You've seen a del operator in regular calculus, and when we talk about that del operator, there's usually an arrow over the top of it, and we're going to maintain that convention. And you'll see when we introduce that arrow in a moment. But for now, for the geometric calculus del operator, there is no arrow over it. And look at its definition. It's very interesting because what we have is we have a unit, the four space-time unit vectors, right? That's what these gammas are. That is the unit vectors in our space-time algebra. And then we have these four partial differential operators, each with a subscript. And so we're creating an interesting object here. It's not a literal member of our geometric algebra, C13. It is not a member of that. And it's not a member because these guys here are differential operators. They're not real numbers. However, we are still using these vector parts, which each of these individually are in fact a member of C13. Every one of these differential, no, not differential operators, every one of the basis vectors are the basis vectors of C13. But the differential operators are not scalars. They're not scalars. They're differential operators. So we've created an object that has algebraic properties of a grade 1 object, right? So the algebraic properties of this will mimic a grade 1 object, but it also has this calculus piece that we have to talk about. And we treat it very much like a grade 1 object because, look, we're going to just use the regular summation convention. And we typically will put, or I prefer, I've seen it done both ways, but I prefer to put the vector part in front, right? Normally, if we had a literal grade 1 object, we would write, some component. Well, I guess it would be, x1 gamma 0, right, plus x2 x0 gamma 0 plus x1 gamma 1, etc., where the component comes first and the unit vector comes second. That's our typical way of doing things. But in this case, we don't want anybody to think that you might be applying this operator to this unit vector, because you can't do that. That's not how this is going to work, and you'll see why in a moment, but that confusion is just too much to bear. So I prefer to put the unit vectors in front of the differential operators, and now we have this open space where we're waiting to act on something. So this differential operator is waiting to act on something. And now we need to talk about, well, what kind of things can possibly go here, and what do they mean? And it's not an easy question, and the paper that we're studying really jumps to the hardest possible answer, talking about manifolds and fiber bundles and Clifford bundles, and I just don't think we need to go there to get where we want to go, which is to unify our Maxwell's equations. So we're going to take a simplified approach, which the paper actually does ultimately get to anyway, and just address now the new question we have now that we've defined our del operator is what kind of things does it act on? So let's talk about that. All right, so let's consider a multivector, which is an element of C13. And remember, C13 is our notation for the entire geometric algebra, and the 1,3 represents the basis, or the metric, the signature of the metric. So our metric has a plus, minus, minus, minus signature is what that's telling us. And so we're considering a multivector just in our geometric algebra. Now, the functions that we want to operate on, right? In other words, the functions that we're going to feed into these differential operators are multivector valued functions, meaning you put in an input, you give it some input x, and the output is a multivector. It's an element of C13 also, right? So now we've taken our multivector and we've kind of turned it into a function. And the output is pretty simple to understand, right? The output is a multivector, some element of C13, which means it's going to have some scalar part plus some vector part plus some bivector part plus some trivector part, which I'll write as the dual of a scalar part or the dual of a vector part plus some where W is a vector, right? Plus some pseudoscalar part, which we write as beta I, where beta is a scalar, right? So that's a scalar, that's a scalar, that's a vector, that's a vector, that's a bivector, and ultimately this is the dual of a vector, so it's a trivector, and this is the dual of a scalar, which is a pseudoscalar. So just as a reminder, right, that's a general multivector, and this function puts out something like that, depending on some input x. So now ultimately we're talking about doing things like this, gamma mu partial mu m of x, right? So this partial mu, right, that's to be understood as partial x mu generally, where x is some sort of independent variable. So clearly this independent variable, that if we're to understand this partial derivative the way we normally do, this independent variable has to be associated with what is inside of these braces here. So what actually is x going to be? What are we going to put in to m to get a multivector out? And there's a lot of art to this, but we're going to take the simpler approach, right? There's two approaches. One is to define a space-time manifold with coordinates, and of course those coordinates would be x mu. And every point in the space-time, we will erect a separate version of the Clifford algebra. And so there'll be a version of the Clifford algebra at every conceivable point in space-time. And then we have to do quite a bit of, basically we're creating a fiber bundle of Clifford algebras or of geometric algebras over a space-time manifold. And the paper actually talks about this, right? I'll show you right here, right? Formally speaking, we replicate the space-time algebra at every point in X on a flat manifold so that acts as a tangent algebra with the multivector, where multivectors can be locally defined. I'm not going to go through all of that. That is part of our lecture series on what is a manifold. So we're going to not engage with it on that level. We're going to engage with it on a slightly simpler level. What we're going to do is we're going to say, okay, our space-time, we're going to say our space-time has the spatial parts and the time part, right? So there's a time axis. This should be 4 dimensions. And everything that sits in space-time can be located with a position vector. And that position vector is going to be x mu gamma mu, right? That is now a position vector for every point in space-time. And this position vector is an element of our geometric algebra. So we are giving physical relevance to certain vectors inside the geometric algebra. We are modeling our space-time with position vectors. And each point will be defined exclusively through these coefficients, which would count as the coordinates of the point. And this is the unit vectors that establish these axes, right? The various axes are established by the unit vectors. And so the function m that returns a multivector is now space-time dependent because we are going to write m is a function of these vectors x, but the vectors x can be written as x mu gamma mu, but mu is this constant object that constructs m itself. So it's totally safe to say that m is a function of just the components of the vector that we insert here. So we insert a vector, but then we sort of rearrange the function's internal guts so that we're really looking at just the components. So we've created a way of putting in space-time coordinates inside our function using this notion of a position vector. And everything stays inside the geometric algebra that we're dealing with. So we don't have to worry too much about this idea of a manifold. Ultimately, we will get there, but not in this lecture. So now if I write del acting on M, this is what I mean. I mean gamma 0, whoops, I mean gamma mu, partial mu, acting on M, which is a function of x nu gamma, well, let's just say a function of x nu, right? And that equals this sum, the sum blowing up the sum, we get this expression. And it looks like we're doing pretty well here, right? It looks like we now have an operator operating on a function where the dependent variables match, right? So I could, if I wanted to take this even further, I could write d dx0 of m, right? And etc. I got to be very careful. My gammas, if I draw my gammas too fast, they tend to start looking like partials. And if I draw it's really more of a problem with the partials. I'll draw the partials too fast, and they'll look like gammas. So it's a bit of a mess, right? But the point is that this now starts to look like it's making sense. I'm taking the partial derivative of a multivector function with respect to a scalar argument. That scalar argument is the components of the vector that is driving the position in our spacetime. So now I have a way of taking derivatives with respect to spacetime. Now the problem is this is still a multivector, and understanding how to take the derivative of a multivector isn't super obvious. So let's start with the simplest possible case and go up from there. You know, before we get to that, actually, let's put a pin in how these derivatives are actually taken for a moment. Let's presume that we know how to do that, but we'll get back to it in a second. I want to talk first about some of the algebraic properties of this derivative operator, of the geometric algebra, or the geometric derivative. We're going to call that the geometric derivative. And let's begin with the idea of factoring out a gamma 0. We're going to factor out gamma 0 from this expression, which won't be hard. The first term, it'll just pop right out. The second term, we're going to have to use the fact that gamma 0 equals 1. Right? So we're going to leave a gamma 0 behind when we factor it out. And what is that going to look like? Well, it's going to look like this. Here's our geometric derivative. We take the gamma 0 out on the left side, so we leave behind a partial 0. But here we've added a term, gamma 0 term, and we took the first one out and we brought it out front, and we left a gamma 0 behind. So this expression here, what that means, as a reminder, is gamma 0, gamma 1. And so we write that as gamma 0, 1. And likewise, gamma 0, 2 is left behind, and gamma 0, 3 is left behind. But we immediately recognize these guys as sigma 1, sigma 2, and sigma 3, the relative unit vectors. So these are actually, remember, bivectors in the spacetime algebra, but they are relative unit vectors and grade 1 objects in the three-dimensional algebra. Now, likewise, we can do this, and that's just a reminder, right? All this should be total review. The tricky part is to understand that these guys just aren't real numbers anymore. That's the part we have to get our head around. Now, you can also take the gamma 0 out on the right side, and you get the same kind of expression, except now you end up with the negatives, right? The negatives of these relative vectors. So ultimately, you have two forms for this factorization. You have the left factorization, and you have the right factorization. And the right factorization, we introduce this negative sign to correct for these superscripts. To flip the superscripts, you have to introduce negative signs everywhere. So that's what we have. We have these two terms. But what we're going to do is I'm going to take this guy, and I'm going to say, you know what? That's a three-dimensional unit vector and a regular partial derivative. We're just going to call that the gradient operator, the 3 gradient. That's what that is. That's the 3 gradient. So this now becomes these two expressions, right? Becomes the time partial derivative in the 3 gradient and the time partial derivative minus the 3 gradient, depending on whether you factor it out to the left or the right, which reveals the algebraic structure of our geometric derivative expression. You're starting to see we're treating it just like a member of the algebra. And what the paper likes to point out, that is, I'm not quite sure how profound it is, but the paper says, well, we've got the gradient operator, we're treating it like a one object, so we should be able to take the geometric product of that thing with itself, which we can write as geometric derivative squared, which is going to be just this guy multiplied by that guy, right? And there that is written out. And of course, this immediately goes away because gamma 0 squared is +1 in our convention. So now you have this, look what you're left behind. You're left behind the same two objects summed. One is summed and one is subtracted. One is added and one is subtracted, which of course is the way you factor something that is square. It's the factorization of x squared minus y squared, right? It's the x plus y and the x minus y, right? So what's interesting is, but here we have the square of something which mimics this structure once you get rid of this. And what does that ultimately leave us with? And it ultimately leaves us with what we know to be the D'Alembert of our regular vector approach. But now the D'Alembert factors into a single perfect square, which is evidently, that's what Dirac kind of wanted to do when he created his formalism. He had to go through some tricky mathematics to find a way to get something that looked like the square root of the D'Alembert, so he could create a structure for the electron based on this notion. Very important idea, I think, but it is sort of beautiful to see that this very elementary algebraic steps get you something that looks like the square root of the D'Alembert. But regardless, even if that escapes you or doesn't seem that profound to you, this algebraic step is still relatively important. It connects our geometric algebra notion and the spacetime algebra with our physics notions and our relative algebra that we've been working with. Okay, so I think that covers most of the important algebraic steps. Oh, there is one other. You want to say, okay, well, we can also, if we're treating this thing seriously like a member of the geometric algebra, I can ask, well, what's the wedge product of it with, say, gamma 0? And that wedge product is going to be pretty obvious, right? We'll just take this wedge straight up, and we end up with gamma 0 wedge gamma 0, so we know that that is going to immediately go to 0. Remember, we're treating this like a scalar. Oh, that should be a 0. We're treating this like it's a scalar object, so it doesn't participate in this wedging. And then we end up with these gamma 0 gamma i's, which is just sigma I, and ultimately this just equals our 3 gradient, right? And likewise, gamma 0 dot del, or dot our geometric derivative, is just going to be the partial with respect to 0. So there's more, and there's probably more algebraic relationships that are important here, but we're just trying to get used to the idea of treating our geometric derivative, right, which is this guy right here, as an algebraic object, setting aside the fact that we have derivatives for their components. Okay, so what next? Okay, so now let's consider the derivative of a scalar function. So the input is still going to be a position vector, or a vector as we understand a four-dimensional vector in our geometric algebra, but the output is just a scalar. So this still counts as a multi-vector function because, remember, a multi-vector function has a scalar, vector, bivector, trivector, and pseudoscalar part, at least in the space-time algebra. But yeah, just consider one that only has the scalar part. That still counts as a multivector, just as a reminder. So there's our multivector. And now we just create this object. So I'm going to make my substitution for delta. Now the substitution I like to make for the purposes of our spacetime algebra is this substitution here. When we study the general geometric algebra, which is I think what I'll eventually do in a separate series of lectures, we're not going to have this, we're not going to immediately drop into this sort of convenient notation. This really only works for the spacetime algebra, or is only used in the spacetime algebra. And a lot of it is used just to give us the comfort of seeing things we recognize from our regular work, which is one of my criticisms of this, is we're actually leaning on our old stuff a lot here. But I feel like it is the way to go. So I'm going to make the substitution for the geometric derivative with this factored form. And then that will give us this form when we move alpha, which is a function of x. I'm suppressing the x here into the operator. So this is the gradient, the 3 gradient operator, and this is just the partial time derivative. So this is easy to understand because this is a scalar function of x, and x0 is a regular real number. So we know exactly how this derivative is regular calculus right here. And this is also regular multivariable calculus. But if we look at it in terms of the geometric algebra, we have this becomes sigma 1 partial 1, sigma 2 partial 2, sigma 3 partial 3, and alpha. And we know each of these is just a function of a real variable, and it's the partial derivative of a function of a real variable. So each of these are real numbers. These are bivectors. However, we treat them as just regular vectors in the three-dimensional algebra. But ultimately, this ends up being a bivector. Well, does that make sense that this part would be a bivector? Well, sure, because we're now going to take this bivector, this geometric product with gamma 0. But each of these terms has a gamma 0 leading in the bivector, right? So we have gamma 0 geometric product with something that looks like gamma 0 wedge gamma I, right? So this this geometric product is going to ultimately just kill the gamma 0, and you're going to be left with a gamma I. So what we have is an object that has the algebraic properties of a vector, which is our geometric derivative, multiplied by a scalar, which should be a vector. And that's exactly what we get. This guy times this gamma 0 is a vector. This part is purely scalar, so it times a vector is also a vector. So we end up with a vector exactly as we would expect just by looking at this basically a geometric product of a vector with a scalar. So that one's pretty easy to understand. All right, now let's consider a vector function where the input is a vector and the output is also a vector. Now remember, the input we're considering a position vector in our space-time model, but this output could be any other vector. So we're looking for the geometric gradient or the geometric derivative of this vector function, where now I've suppressed the variable x right here. And let's just first, before we really dig in, I guess we are digging in, but let's just blow this thing up and see if we can get any more insight regarding how our geometric derivative actually acts like a one-grade object. So I'm going to make the direct substitution, right? So this part here is directly the definition of the geometric derivative, and the vector, we're just going to blow up into its components right here, right? So those are the two pieces of our geometric derivative of this vector function. Then we are going to commute the things that look and behave like scalars. In this case, this is a scalar, this v is a scalar, and this is a derivative operator. And this is a function, right? Remember, this guy v of x is a function, but it does return a vector, and that vector is ultimately V, mu, gamma, mu, right? So these guys here are also functions of the coordinates. So this is a partial derivative of a function. So we can actually take that partial derivative in principle. Given mu and nu, we could take that derivative. Um, the Because this guy here is a scalar, right? It's a component of a vector. So it's a scalar. So all of the algebraic properties reside in this expression, this geometric property of these basis vectors and their duals. So if we blow that up, we know the geometric product of these two things is going to be this inner product plus this outer product, right? That's a fundamental thing of two vectors in the geometric algebra multiplied together can be broken up into this symmetric part and this anti-symmetric part, which we define as the inner product and the outer product. And then our partial derivative lives outside the brackets. But this, because we're dealing with a vector and its dual, here we'll get this delta function, mu nu, and then I'll bring this piece back in over here. So we have this delta function, and we have this derivative. And then here, I left this part alone. I guess what I needed to do was get rid of these brackets here, right? So now it looks like we have this outer product multiplied by what is a scalar process, right? This is going to be the partial derivative of a scalar function. So that's scalar. So this is a bivector piece, and this is a vector piece. Then I execute this delta function, and we're left with the partial mu, and the superscript here is mu. So that is just a uh, uh, a divergence, really, but it's going to ultimately be this expression, this del dot v, right? This del dot v. If you execute the algebra of del dot v, you get this expression. And here, if I now move this guy to become the coefficient, I move our scalar piece to become the coefficient of this part, I end up with the definition of the derivative, and I leave the vector part behind, and this reconstructs the full vector v, and this reconstructs del, so I get, this reconstructs the geometric derivative, so I get this piece, I get the anti-symmetric part. And that is exactly how you would expect an object, a grade 1 object, acting on a vector to behave. If that's a grade 1 object, and that's a vector, the geometric product has the same form we've always used to expect. So that's totally cool. So that's just, I'm just sort of breaking down the more of the algebraic nature of this del operator. But let's take a closer look on how this product would actually manifest itself. So to demonstrate this, we're just going to make direct substitutions for what we know to be the algebraic structure of the gradient of the geometric derivative and a vector. So the geometric derivative, we're just going to immediately substitute this known form right here. And you might say, well, wait a minute, in the known form we did, the 0 was up there. But remember, in our convention, gamma 0, gamma 0, gamma 0, that equals 1 by definition, actually. And between that and this fact, that gamma 0 geometric product gamma 0 equals 1, we know that gamma 0 equals gamma subscript 0 equals gamma superscript 0. So we can make that arbitrary change. On the other side, we have v equals v. We'll write v in the well, I guess we'll write it in the normal form. v0 v0 gamma 0 plus vi gamma I, and then we factor out a gamma 0 from this. So once we have this, we can factor out a gamma 0, so we'll get gamma sub 0 v superscript 0 And we have to, since we have gamma 0 equals 1, so we have to leave a gamma 0 behind. So we'll end up with gamma 0, gamma I, VI, like that. But this is minus sigma I, so we end up with gamma 0, V0 minus the vector, the relative vector V, right? So that's exactly what we want right here. And oh, it's not exactly, because here we have a subscript 0 and here we have a superscript 0. But again, in our convention with our metric, the 0 component can be exchanged arbitrarily with subscript and superscript. So we just drop the superscript. And this matches what is done in our paper. Okay, so now we're going to blow this up and we're going to get a very simple expansion. Now, we have to remember a couple things. We've done this before when we first studied relative vectors, right? Relative vectors live and operate in a three-dimensional geometric algebra. And this guy over here is clearly in our spacetime algebra. STA is a typical abbreviation for spacetime algebra. So we want to take advantage of the fact that we have this three-dimensional spacetime algebra to work with. So typically, just as a reminder, when we think of the basis vectors, gamma mu for the spacetime algebra, with a metric with a signature, with a metric signature 1, minus 1, minus 1, minus 1, right? That's our sort of metric signature. And we think of the three-dimensional algebra as just sigma I with a complete 1, 1, 1 metric, right? And these guys are regular vectors. They're grade 1 objects. They're 1 grade objects in the 3D algebra, but they're bivectors in the spacetime algebra. I know we've gone through this a lot, but it always confuses me, so I assume it confuses everybody. That's probably a bad assumption, but so we're going to treat this process up here as much as we can inside this three-dimensional geometric algebra. So when I see an object like this gradient object, this 3 gradient, well, that's sigma I partial I. That is a vector in the three-dimensional algebra. It's a bivector in the spacetime algebra, but it's a vector in the three-dimensional algebra. This V with a bar over it, well, that we've constructed to be a vector in the three-dimensional algebra. So this concept, this thing is now sigma j v with a little j there. This object here is the product of a vector times a vector in the three-dimensional algebra. It's also a bivector product in the spacetime algebra, fair enough, but we're going to work as much as we can in the three-dimensional algebra because it's actually a bit easier, but also we're headed that way. We're trying to link up with Maxwell's equations, so we want everything to look like three-dimensional vectors as much as we can, and we're making some progress. Okay, so with that aside, let's move on. And we're going to immediately take advantage of this, what I just said, by treating this as a geometric product of two vectors. So this is going to immediately blow up into this inner product plus this wedge product, right? Because it's two vectors, right? So that's the definition of the geometric product of two vectors. It's got a grade lowering piece, or a symmetric part, a symmetric grade lower, and a anti-symmetric grade higher piece. And that's exactly what we're going to do. And now I'm going to take all of this stuff and we're going to mix it by quality, by type. For example, that is the partial derivative of the component of a vector. So this thing is a scalar. It's a scalar function. You got to remember now, v is a function of this vector, this inserted vector mu. So v is a function of space-time in the sense that we've defined space-time to be a position vector as the argument of our function. So in other words, I've suppressed x. This should read delta v x0, x1, x2, x3, like that. So this partial derivative is the partial derivative of a scalar, or is the partial derivative of a scalar, because we're now looking at the v0 component of this object, right? So this is a scalar. That's my point there. So I will circle that in red because it's a scalar. Now this next object is the partial derivative of a vector. So if you just blew that up, you'd have the partial derivative of an object that looks like v0 gamma 0 plus v1 gamma 1, etc., right? So you end up taking partial derivatives of the components, but you're not taking partial derivatives of these unit vectors, so you're leaving the unit vectors behind. So this object here is a vector object. It's a vector object. Remember, all in the 3D, right? We're thinking in the 3D. Now, it seems weird. We're thinking in the 3D in terms of the algebraic property, but notice this subscript is still the time subscript of the spacetime algebra, right? So it's a little bit delicate there, but not so bad. I can track all that. So let's keep going, and now we're going to study this part. Well, this is a vector multiplied by an object that's a scalar. So this is obviously a vector, right? This is obviously a vector. This has this 3 gradient has the algebraic properties of a vector in the 3-dimensional algebra. So that is a vector. And that leads us with, well, these two parts. This is a vector dotted with another vector. Clearly that's a scalar. And this is a vector dotted with a vector. So this is a bivector. So I'm going to circle this part here in red because it's a scalar. And then this bivector part I'll circle in blue. Okay, so now we've kind of chunked it up. Now I'm going to reorganize it so it's organized by grade. So here's the grade organization. This is the scalar part. This is the vector part. This is the bivector part. Now let's consider, I hate to do this because I know I'm going to screw it up, but remember our original piece here is the gradient, is the geometric derivative of a vector. And we've decided already that this acts like, this guy here already acts algebraically like a vector. So this thing really needs to be, in the spacetime algebra, del dot v plus del wedge v, right? And this part is scalar, and this part is bivector in the spacetime algebra. And that's not, and just to be clear, that's not too demanding in the sense that, well, that's scalar for sure. And these two are not scalars for sure. So this part is definitely linked to that part. But let's make sure that the rest of this stuff is a space-time bivector so we can link it to this piece. Now, this first part here, the part in green, well, these are 3D vectors, but we know 3D vectors are composed of objects that look like sigma I or sigma lowercase I, which would be gamma 0I or gamma I 0, right? So these guys are in fact space-time bivectors, no problem. So the green definitely belongs in this grouping, the space-time bivectors. Now this part, it doesn't take too much thought. It would look like you're dealing with a bivector, right? Times wedged with a bivector. So you'd think that this might be a pseudoscalar, and I even made this mistake myself a couple times. But it turns out that it's always going to be a bivector of the form sigma sigma I sigma j, something like this, right? which is always going to be gamma 0I, gamma j0. And by the time you work through all of this, these are geometric products. So this is going to be gamma 0, gamma I, gamma 0, right? And then we know that the gamma 0 we could just lift, and the gamma I we can lift if we add a negative sign. And then we commute this 0 through twice, get rid of it, and we have, oh, this should be a j, I think. A j, yes, sorry, this should be a j. And the point being is that we're always left with a gamma ij. We're always left with a bivector. So it, as a matter of practicality for this calculation, this piece that looked like it might have pseudoscalar potential isn't. It's always a bivector. So it always belongs in there. And so what we're seeing now is that we've got, this is a total divergence in the space-time algebra. And this part represents some kind of generalization of the curl in the space-time algebra using the geometric algebra. That's a little less obvious until you substitute this away, and we're looking now, remember, we want to lean on our 3D geometric algebra. So we want this to look like a cross product. So let's see if we can get this to look like the cross product, which is not very hard. The first thing is we remember the definition that in the 3D geometric algebra, if I have two vectors A and B, the cross product that we're so familiar with is the wedge product multiplied by the inverse of the pseudoscalar. So it's a dual of the wedge product. So the wedge product is a bivector. It's dual, that means the part of it that doesn't have this -1 on it, that would be the dual of it. But we define it with the inverse there. So, and usually in the algebras we deal with, I squared equals -1. So I inverse equals -I. So sometimes you will see this written this way if they're talking about a particular space-time algebra, for example. But the point is that the wedge product is this cross product, which, remember, the cross product in regular Gibbsian stuff is a vector. So the dual of a vector is a bivector. So that's what we have. We have a bivector on the right, and the dual of a vector on the left makes perfect sense. So this guy here can now be substituted away like this. We now have this term, del cross v. Now that cross needs to be unambiguously a cross. It kind of looks like a variable x. So I want the cross product, right? Now I could put parentheses here, but the standard rule is geometric products are always done last. So this cross product would be done first. And so the order of operations makes this notation right here just fine. So now I've actually introduced a cross product. Oops, I guess one thing I'm missing is a little vector over the v to make sure you know it's a relative vector. Those arrows are actually really important now. So this expression, our final version of this expression, looks like this right here. Okay, so that is how we take the geometric derivative of a vector in the space-time algebra. Okay, so that's where the fun began, but now this is where the fun really takes off, because we are now interested in the geometric derivative of bivector fields. And the reason this is now important is we have to remember our electromagnetic field we want to model as a bivector field. So the electromagnetic field bivector is we're going to write everything down in very suggestive notation now. So E is going to be a relative vector, just given by EI sigma I. So this is a bivector in the space-time algebra, but we're writing it down as a relative vector. And B is another relative vector, but the F is going to be the sum of the the two, but B, it's going to be the dual of B. And what that, just as a reminder, how that works is all of the sigma i's are defined as gamma 0, gamma I. But what we are looking for the magnetic field is always the dual of this. In other words, we always need, the magnetic fields always have to be something like sigma j, gamma j, gamma k, gamma j, gamma k, both spatial, right? There's no gamma zeros in the in the magnetic portion of the magnetic field tensor. So we're going to model ultimately the magnetic field as a vector in the three-dimensional geometric algebra. But when we start working with it, we're taking its dual and we're adding it to the electric field, which is a relative vector. And we end up with our model for the electromagnetic field tensor. This is a bivector, right? It's always going to be a bivector because the dual of a bivector is a bivector. This is a bivector by definition. E is a bivector by definition. So now we're looking for the derivative of f. So let's play around with that. Well, here we go. We are taking the geometric derivative of a bivector f. Let's just treat everything algebraically and see how far we can get. We're going to substitute this expression right here on the left-hand side for the geometric derivative. So we have this scalar operator and this relative vector operator. And on the right-hand side, well, that's what f is. F is this bivector. I know we're going to run into this problem over and over again. It's a bivector in the space-time algebra. It is a, but what it is in the 3D algebra, this is a vector in the 3D algebra, and this is a bivector in the 3D algebra because it's the dual of a vector in the 3D algebra. But in the space-time algebra, this whole thing is all one big bivector. Okay, so with that in mind, now we just multiply this thing out and we do the obvious thing. We get this partial derivative, this first term, then we have these two cross terms, and then we have the final term. And notice that this pseudoscalar just follows everything like it's a constant. Everything, it just follows through this problem like a constant. And the next step is to treat it like a constant. Now I'm going to pull out the pseudoscalars where I find them. So the pseudoscalar exists here and the pseudoscalar exists here. But anyway, the first term doesn't change. The second term, I just sort of pull out the pseudoscalar because it's not subject to the derivative. And in these two cases, we have these derivatives of vectors, but we know how to do that, right? Because the vector E is just going to be E0 sigma, well, not E0, right? Because this is this is in the 3D algebra, E1 sigma 1 plus E2 sigma 2 plus E3 sigma 3, and E1 is a function of x, and that's a derivative of that argument. So we're going to be taking the derivatives of these component terms, and what's going to be left behind is a vector. So inside these braces, I guess there's another bracket over here I've forgotten, because this whole thing is multiplied by gamma 0, right? So inside these brackets, this is a vector. It's a vector, but the derivatives that we're taking are always derivatives of scalar functions. Likewise, this is a vector. The derivative of b is a vector, but it's going to be the dual of that ultimately, right? So that will ultimately look like a trivector in the space-time algebra and a bivector in the 3D algebra. This should ultimately be in the 3D algebra a scalar term, right? This has got to be a scalar. This is going to be a bivector in the 3D algebra. This is going to be a scalar in the 3D algebra, and this is going to be a bivector in the 3D algebra. And now we can start seeing Maxwell's equations in here, right? If we treat our electric field and magnetic field literally with E and B, well, we have a time derivative of the electric field. We have a time derivative of the magnetic field. We have a divergence of the electric field and a divergence of the magnetic field. And we have a wedge product here and here, but we just saw how to convert wedge products to cross products. So we have a curl of the electric field and a curl of the magnetic field. So we can clearly see that the derivative of F, when it's decomposed, has all the pieces of Maxwell's equations inside it. And that is very exciting because clearly that is how we're going to get to our final goal, which we're zeroing in on very closely. Okay, so what next? Okay, so the next step is going to be to rearrange this so we isolate all the terms that are duals, meaning we take all the factors with the pseudoscalar to the right, and we replace all of the wedge products with cross products. And that's not so hard. I just did it right here. This term has no duality, no pseudoscalar. This term has no pseudoscalar. This term, when I convert it to a cross product, will have a pseudoscalar. But this term, when I convert it to a cross product, will introduce a pseudoscalar, which will multiply by the one that's already there, giving me a -1. So that accounts for that minus sign. So this minus sign here comes from replacing that with del cross bi, right? So you get del cross bii, and those two i's give you a -1. And then obviously this term has a pseudoscalar, and that comes right to here, right? So this term ends up there, and this term gets its pseudoscalar, so it comes there, and then the del dot b. Oh, wait a minute. I've got that backwards, right? It's this term goes here, this term goes there, and then this guy obviously has a pseudoscalar goes there, and that's where the pseudoscalar lives. So we're all good with those splits. And now, what have we got? Well, this is a 3D geometric algebra vector. This is a 3D geometric algebra scalar. And this is a 3D geometric algebra bivector. Likewise, 3D geometric algebra vector, 3D geometric algebra scalar, and 3D geometric algebra bivector. So both of these pieces, the piece that's, well, then each of these, of course, is given a 3D duality transformation. So this scalar becomes a pseudoscalar. This bivector becomes a vector, right? And this vector becomes a bivector. So yeah, and that's the way we expect. We expect magnetic fields to always be bivectory. We expect electric fields always to be vectory, right? So, and you can see right in here, these are all the parts of Maxwell's equations. These are time derivatives. Remember, gamma zero or partial zero is with respect to time. Time is the zeroth component. So here's our divergence of a magnetic field, the magnetic vector field in the 3D algebra. There's the divergence of it. There's the curl of the electric field, the curl of the magnetic field. All of those things show up in Maxwell's equations. So now the question is how do we tease them out to actually look like Maxwell's equations? And let's just do it and call it a day. So step one, we want to reorganize this so that we have the scalar parts and the vector parts and the bivector parts in sequence, so we can kind of sort them in our head. Let's do that first. Okay, so that was pretty easy, right? All we have to do is swap things around. I did a little color coding. Scalar parts are in red, vector parts are in green. And when I say vector, I'm talking about the 3D algebra, right? The 3D algebra. So now we have, this is the geometric derivative of our electromagnetic field is written like this. So now, what do we do next to sort of pull out Maxwell's equations? Well, if we're looking for a formula, right? So this is just a definition, really. All we've done is define things and move things around. We haven't interjected any physical principles in here. We're saying our field is modeled by these things, and we're calling F the electromagnetic field um, uh, uh, bivector, but we haven't said anything about it. We've just this is true by definition, right? So if I was going to assert some physics, I might be inclined to do this. I might be inclined to say equals 0, right? So to make it a little bit tighter, I might be inclined to write the geometric derivative of f equals 0. And what will that get me? Well, the first thing it would get me is this side, this left-hand side, is all kinds of different objects, right? When I say this is a scalar, when I say del dot B is a scalar, I'm actually forgetting about the I. It's really a pseudoscalar, right? It's a pseudoscalar. And the only true scalar here is del dot E, right? When I say when I say the time derivative of B plus the curl of E is a vector, again, I'm forgetting about this I out here. It's not a vector. It's actually a 3D bivector, right? So this part here, I'm now going to circle in blue, right? I'm going to circle this in blue. That is a bivector. This pseudo-scalar, I'm going to circle in, let's say, squiggly blue, maybe? How about that? I'll squiggle it around. So that's a pseudo-scalar, right? Then this red piece here, this really is a scalar. And this part here in green really is a vector. So I have a bivector piece, a pseudoscalar piece, a vector piece, and a scalar piece. Now you say, oh, wait a minute, you forgot about this. This turns everything upside down. This turns your scalars, this gamma 0 turns your scalars into vectors, your vectors into bivectors, and things like that. But remember, I'm setting it equal to 0, right? So I'm going to multiply both sides by gamma 0, and I'm going to get rid of this gamma 0, right? Because remember, the gamma 0 is actually multiplied by everything. You see a factor of gamma 0 here, and you see a factor of gamma 0 there. So that gamma 0 will go away, and I'll be left with everything exactly as I described. So let's write that out. And so once I've done that, I end up with the scalar part in red, the vector part in green, the bivector part in blue, and the pseudoscalar part in black, and each all equals 0. And of course, the next step should be somewhat obvious, is that in order for this to ever be true, each one of these parts has to equal 0 by itself, So I immediately recreate Maxwell's equations in a vacuum. I get del dot E equals 0. I get the time derivative of the electric field minus the curl of the magnetic field equals 0. I get the time derivative of the magnetic field plus the curl of the electric field equals 0. And remember, since this term has to equal 0, that I just goes away, right? I end up pulling it, multiplying both sides by I and dividing through by a negative sign. So I get that equaling 0. And then I get, finally, the legendary and famous del dot B equals 0. And of course, in a vacuum, this is Maxwell's equations in a vacuum. And the paper actually cites that, right? So this is from the paper that we're reading, right? Maxwell's equations in a vacuum, del dot F equals 0. F is our model for the electromagnetic field, and it's modeled exactly the way I described. And they break it down into two parts, right? We have del dot F equals 0 and del curl F equals 0. And of course, this is true because we're dealing with the 3D, the relative algebra, right? But ultimately, it breaks down exactly the way we broke it down. The divergences are both 0, and these curls are completely symmetric, but that minus sign is just perfectly there. It's there and it belongs there. So that looks really great. So we're almost finished because now we need Maxwell's equations that are not in a vacuum, right? Maxwell's the general Maxwell's equations that has charge density and current density in it. So that's not a very big step away, right? All we need is something on the right-hand side to model charge and current density. And so now we're going to look for a model for charge density and current density and put it on the right-hand side. And of course, that's just going to be yet another piece of the geometric algebra. So let's take care of that. So the next thing we would think of is, okay, well, if that's Maxwell's equations in a vacuum, what if I say it's not in a vacuum and I say there's some current out there? And I now model the current density with J, a vector J. Let's go with a vector. So J is going to be J mu gamma mu. And then we do the usual process, J mu gamma mu. Ultimately, that's going to be gamma 0. We factor that out, and we have J0 plus Ji sigma I, right? So I do the space-time split that we always do. And that now becomes my J mu gamma mu. Well, you may remember that 0 term before that there is a gamma 0 floating around over here. So if I put the J over here, I have to sort of return that gamma 0 over on the far left. So if I now replace this with its space-time split, I have a factored gamma 0 on both sides, and it all goes away. So what is that ultimately going to look like? And with this, all we do is the same thing we did before. I guess this is a scalar part, and this is a vector part. So the only thing that changes now is I have delta E equals what we're going to call the J0 piece. And that's the scalar part. And then the vector part, partial 0 E minus the curl of B equals Ji, right? That'll be the vector part. Well, I guess I should write that a little more. This wouldn't be Ji, it would just be J, the 3 vector, right? Because this is actually equal to the red part being the scalar, J0, and then the green part plus J, the vector piece, right? And then these two actually remain the same, right? You still get the curl of B equals 0 because there's no pseudoscalar part over here. And there's also no bivector part. So you still have the time derivative of the electric field vector plus the curl of the electric field equals 0. And so now it's just a matter of connecting J to the units that you're choosing, right? So for example, I will go to the paper that we're actually reading. They do that. The paper really takes a few extra steps to get to where we want to be. They include magnetic current and a few other things. So how would that translate? Let's take a quick look. Right. So if you in their formula, in the formulation in the paper, they include magnetic charges, right? So I'm definitely not going to worry about that. So let's get rid of some of that stuff. And they also use a part of a potential formulation in their explanation, which we didn't need because we're just demonstrating this. So with no magnetic charges, right, this of course goes to zero. With no magnetic charges, there can be no magnetic current, and so that goes to zero. And then you're just left with the units that you choose, right? And they're choosing the units. Um, they have a factor of c works in there. Remember, our derivatives, our sub-zero derivative uh, is the same units as space. I wouldn't worry too much about the units. They do a very nice job of helping with the units in the paper if you really care about it. But just understand, we did when our analysis, we didn't go through this potential formulation that they did, which is pretty interesting, but um, it's not super relevant. Oh, I do notice a mistake we made, right? See the minus JE there, the minus JE? That's important, right? What did I do? Hold on a second. Yeah, see, remember when we take out this gamma zero, that should be a minus sign, right? So that should be a minus sign. Let me erase that, change it to a minus sign, which means this here is a minus sign. And ultimately, the minus sign finds its way right down into the equation itself. So that should be a minus sign. And I think that will agree with what they wrote here. Time derivative of the electric field minus the curl of the magnetic field is the opposite of the current, the electric current. And is that what we have? We have yes, that's exactly what we have. So there you have it. So ultimately, now we can write del, or the geometric derivative of f equals j. And with that, we can go back to our first page. And this was over an hour ago, but you remember this, right? Here's our Maxwell's equations in full-blown form. Here's our uh, exterior calculus form. Here is our Lorentz invariant relativistic form. And this is the missing magic thing that we finally, after all this time, are able to write del f equals j, right? And this is a 4-vector, and this is the electromagnetic field bivector, right? And this is the geometric derivative. And there you have it. We've got it down to one little formula. So that was a long journey, and I am going to call this mission complete, meaning I probably will not be returning to the rest of the juicy stuff in this paper. It was delightful. I do plan to study this in a separate class. I think I'm going to redo all of geometric algebra in a new context, maybe using some new software that I've got and I've learned how to use. But look at how much more material is in here. I mean, this is a 100-page paper, and we really left out some juicy stuff, but to get to where we wanted to go, the hard part was just learning about space-time algebra, and we did a very thorough job. So thank you for sticking with this lecture series, and I hope to see you in the next one.